this lesson, we're going to work on probability and odds. Essentially just writing down some ratios or writing down the fractions that would fit theoretical or experimental probability, finding odds in favor or finding odds against. And for the most part, it's really straightforward. It's just, do you know what the definitions are? Because the work itself is pretty straightforward. You ought to know that theoretical probability is nothing more than the ratio of the number of favorable outcomes compared to the number of possible outcomes. A lot of times people will just reference it as successes over outcomes. So really all that we're doing is counting. If you can count how many ways there is to find success and how many different outcomes there are, you just got to create a fraction. So on a regular die, or six-sided number cube, remember die is the singular form of dice. What's the probability of getting something that's even? Well, keep in mind that even would be 2 or 4 or 6. So how many different successes are there? 3 successes. How many total outcomes are there? 6. 1, 2, 3, 4, 5, 6. That's our probability. Keep in mind that probability we would always expect to be simplified, so when we divide out by our 3, we simplify it down to just 1/2, and we're done. What about here? The probability of getting 4 or 6. Okay, well, keep in mind what is considered a success. 4 would be considered a success, or 6 would be considered a success. So 2 successes out of 6 possibilities leads us to the probability 1 to 3, 1/3, 1 out of 3. What about the third one? Probability of 4 and odd. Every once in a while, this trips people up because you got to pay attention to the word and. The presence of the word and is telling us that we have 2 conditions and we need both of them to work. Well, how many numbers work for the condition of being 4? Obviously, just that one number. 4 is the only thing that matches with the 4. But then we also have the second condition of being an odd number, and odd numbers on a number cube would include 1, 3, and 5. So how many numbers fit both conditions? That it has to be in the list of 4 and in our list of odd numbers. None of them. Yeah, there are 4 numbers there, but none of the numbers appear on both lists. We're saying we need something to be a 4. Great, 4 works. And it also has to be an odd number at the exact same time. And there's nothing that does that. Nothing can be both a 4 and an odd at the same time. That's why you've got to pay attention whenever you're working with probability to things like and, saying both of them have to work, versus an or, where if you're working with the or condition, we only need one of the 2 conditions to work. Either one is acceptable. Difference between or versus and. Experimental probability, very, very similar to theoretical. And that one is simply number of successes, but instead of the total number of outcomes, the number of trials that it takes to happen, or how many trials were conducted. Here's a really simple one. Actually did happen. I was playing Skyrim last night, and I wanted to pickpocket a necklace of sneaking from Naranya in Windhelm. And people are like, shut up, Brian, your nerdism. Too bad. Nerdism is a good over. Alright, so I wanted to steal it, and because I had a low pickpocketing skill, and I knew I was going to wind up getting caught a bunch of times, so I was doing like a save and load technique so I'd be able to actually pull it off. Yeah, it's cheating. I don't care. I did it anyway. But it took me 14 tries before I was able to successfully steal this thing. And if you care, the game said it was at 4% probability of being able to successfully steal it. Well, does my experiment match the theory?
No.
Okay, well, experimental probability, number of successes. So the probability that I was able to pickpocket successfully, how many successes did I get? Just the one. I didn't reload it after I successfully stole from this lady. But then it took me 14 trials to get there. And of course we know we'd actually be able to take this stuff and, I mean, we could turn it into a decimal or a percent simply by taking 1 divided by 14. And it's 0.071. So that's a 7.1% probability based on my experiment, when the game said I had a 4% chance. So kind of an indicator that I got lucky and managed to get it quicker than we'd expect. Similar type, out in Bozeman, they've got a golf course. And you go pay for your mini golf, and the last hole, if you can actually manage to get a hole-in-one on the last hole, they give you your money back. So you get some free golf if you pull off the hole-in-one. Well, making up some numbers, let's say last week, 24 out of 256 people got this hole-in-one. What's the probability then that you get a free game of mini golf? Okay. Probability of our free game. How many successes were there?
24.
24. How many trials were conducted? 256. That's our probability. 24 out of 256. Please remember though, we do expect you to simplify these. What number will divide into both 24 and 256?
20. 10.
Okay, you should be able to recognize at the very least, they're both even numbers.
4. 6. 2.
So we can divide out by 2,
6.
which would give us 12 and 128. 6 actually won't work because 6 does not go into 256.
That's what I was just checking.
It's a good guess, but it's one that doesn't actually check out. What about 12 and 128?
8.
Well, they both have a 4 that goes into them. So dividing those, 12 divided by 4 equals 3. 128 divided by 4 gives us 32. And this is the big reason why we want them to be simplified. Because when you tell people, oh yeah, 24 out of 256, they don't instantly start thinking, well, that's, when you're working with bigger numbers, it's harder to have a mental image of, well, is that a lot? Is it a little bit? When you simplify and you break it down to something like 3 out of 32, it's easier for people to get a mental image of, is that a big percentage, a small percentage, is it a high probability or low? It makes it easier for people to understand with the simplified fraction. That's why we always simplify it. All right, for our basketball players, consider here. Let's say that you're practicing your free throws at practice last night and you made 20 out of 32. Tonight, you're planning on shooting 75 to get some extra practice in. Make a prediction on how many free throws you're going to make. Remember how we spent all of our time working on setting up proportions and solving them? We can still do the exact same thing here. Recognizing that we would have our experimental probability, 20 made out of 32 taken, we could try to make a prediction as to how many you will make out of 75 taken. Cross multiply, solve, we've got our solution. So with this one, we'll multiply 32 times m, 32m, 20 times 75 gives us 1,500. And of course we know what we'd have to do to solve this one. When we divide out by 32, okay, save us a bit of time, let's grab a calculator. 1,500 divided by 32. And that gives us 46.875. Consider that for a second though. You don't leave that as your final answer?
Heck yeah.
Yep. Of course not. How do you make .875 free throws?
Some of it
In this,
you barely
in
make.
this situation, you're not able to say, well, he made a fraction. It's not like, oh, the ball got stuck up behind the rim fry, and that counts as 3/4, 7/8 of a free throw. You don't get 7/8 for points. If it gets stuck, it's still a miss. So this is a piece that we know it's not possible to get an exact one, so we're going to round it up and say our prediction is going to be 47 made free throws. Is that a guarantee? No, of course not. You could have a good night shooting, and maybe instead of making 47, you'll actually make 60. What if last night, the 20 out of 32, what if last night you were ice cold and you're normally a whole lot better than that? We would expect higher here. Depending on other factors, we don't know if you're going to make exactly 47. You probably wouldn't, but this is just based on the information that we have available. This is our best guess that we can make right now. One topic that's very, very similar to probability is odds. The big difference between probability and odds is actually the definition of the ratio. When you were doing probability, we said it was the number of successes over the number of total outcomes. This one's different. When we are looking at the odds in favor of something, so the odds of likelihood, it's actually favorable outcomes over unfavorable, or more simply, your number of successes over the number of failures. Not successes over total, successes over failure. Just as easy to calculate, but you have to make certain that you are paying attention to what the definition is. And it gets compounded a little bit because there's another type of odds as well. Instead of odds in favor, we can look at the odds against something. So the odds that it won't happen. When we're looking at the odds against, it's just flipped. Failures compared to successes instead of successes being compared to failures. As long as you know these two pieces of vocabulary, we can get our answers pretty quickly. So consider here, getting ready to go play bingo. What are the odds in favor of drawing a B? Keep in mind, when we are looking at odds in favor is the number of successes over the number of failures. So when you're playing bingo, how many ways are there to get a B compared to not getting a B? Well, how many successes are there? How about right there? You get the B for bingo. One way. One letter. And your INGO, I-N-G-O, those are the other ways to get something that's not a B. So this one then is not a probability 1 out of 5. It's the odds 1 to 4. Still based on counting, but instead of counting total outcomes, we're counting failures. Similar type problem. What are the odds against getting something in the 50s? Different problem entirely here. Still based on bingo. Odds against are the number of failures over the number of successes. What would we consider a success then? Getting anything in the 50s is considered a success. So of course we've got 50, 51, 52, 53, 54, 55, 56, 57, 58, 59. We have 10 numbers in the 50s, so this is indicating to us that we have 10 successes. Well, if there are 10 ways to get something in the 50s, how many ways are there to fail? keep in mind that bingo has 75 numbers.
24.
You get rid of 10 of them that are successes,
62.
and that's going to leave you with 65 failures. When we build our odds against, all we have to do is create that ratio, the number of failures compared to the number of successes, and those are our odds, 65 to 10. Of course, 65 to 10 is still a ratio we can simplify. We divide it out by 5. We've got the simplified ratio, 13 to 2. Our odds against getting something in the 50s in bingo is 13 to 2. Please observe then that whether you're doing odds against, or you're going with odds in favor, or if you're calculating probabilities, they are all very, very similar to each other in that you will create ratios. You have to know how to create the ratio based on their various definitions. And it is also possible, using those ratios, to set up and create proportions so that you can make predictions on things depending on the context of the problem.